All right, friends and neighbors, welcome back to another networking video. Hey, remember, we started on a bit of a journey, right? We wanted to go through TCP and UDP and IPERF from the ground up, and we wanted to really tear into that because, you know, we've done a lot of videos, we've done a lot of content here, but we're trying to really get down into the weeds on some of these ideas. Now, last time, we went through a basic capture and we introduced or reintroduced the handshake, right? Sin, synac, ac. And then we talked about the things that are part of the handshake. And so one of those things was the window. And so we talked a little bit about that and we opened up on what the window size actually looks like. Today we're going to take a look at another capture and then introduce yet another process that's going on. So let's go up to the next floor in our conversation in TCP, UDP, and IPERF from the ground up. So remember that we have that handshake, right? The sequence and acknowledgement numbers, right? That part of the purpose of that handshake is to establish those numbers, but then we've also got the window size, and then we are also going to figure out what options the two sides are going to agree on. But maybe a good thing to do is to remind ourselves what the window size actually is. So the RFC 793, or now the RFC 9293 definition of window size, is the number of data octets beginning with the one indicated in the acknowledgement field that the sender of this segment is willing to accept. In other words, my receive window. So I'm going to send you a window. So you get it from me, and I'm telling you how much data I'm willing to accept. And at the same time, you are telling me how much data you are willing to accept. Now, there's a calculation here, right? There's a certain number of what we call bits in flight. If you were a long way away from me, I could have sent you a whole bunch of data, and there's a whole bunch of data in transit. Now you're getting some of that. You're going to try to acknowledge some of that, but there's a delay here. And so the delay, or the bytes that are out there, we call those bits or bytes in flight. And so what I have to do is keep track of what you sent me and what I've sent you, and trying to make some calculations on how we should handle the transmission of the next chunks of data. Now, TCP is also concerned with congestion. We don't want to send too much data into the network. And certainly when we start to get into scaling factors for our window, we have the ability to send a lot of traffic into the network. And so we're worried about congestion as well. So TCP has this sort of motto, right? Be conservative in what you send and liberal in what you accept. So we want to limit ourselves as to what we're going to put into the network and be willing to accept a lot of data. Okay, so with that reminder, let's take a look at another capture. Now here's a capture that I very commonly use with my students because it's really easy to see what's going on in this capture. So we start right at the beginning here. We can see our handshake, right? We have a sin, synac, ac, and that is our handshake. And remember that on one side, I'm going to say, well, not only is this the start of a conversation that I'd like to have, I'm going to set my window. So if we put 16,384 in our calculator, and we're just going to remember that for a sec. Now the opposite side is going to say, well, my window is 4128. Now this is the server side. Now we don't typically send a lot to a server. Typically it's we're pulling from a server, or we might say that the server is pushing to us. But the server is also going to have a window size. So both sides have a sequence number. Both sides acknowledge that with the acknowledgement numbers. Both sides have a window size. Now, in addition, I'm going to say what options that I'm willing to, or that I would like to use for this particular conversation. So these are mostly the basic ones that we see in the original RFC. We've got this additional one here, but we're not going to worry too much about that right now. Okay. So we get to the end of our conversation and we take a look here. Hold on a sec. The client, right, 1.1 in this case, has changed the window size. Now we'll talk more about that, what that means here, but for right now, all that I'm going to do is say that my new window size is actually going to be 17,520. Okay? All right. Now what's the next thing that happens in this conversation? Well, the client wanted the connection. What did he want the connection for? In this case, it's a web server, and so the client says, hey, here's an HTTP GET. Now it's still TCP, right? We can still see that. We collapse this, still TCP, but it's an HTTP GET. Now there's a couple of details that we wanna track here. One is that this is actually data. The other thing is that we do the SYN, SYNAC, ACK, and the next thing that I see is not from 1.254, but it is from 1.1. So I see 2 packets in a row that are from 1.1. So just because you're having a conversation doesn't mean it's 1 packet this way, 1 packet that way, 1 packet this way, 1 packet that way. They agreed to have a conversation, and 1.1 says, okay, cool, now that we're starting up, give me this. And it is a website. Now, if we take a look at something here, let's take a look at what the server said its window size was, 4128. So I guess we'll do that one first. So we put 4128 in our calculator. Now, the client says, here's an HTTP GET for you. How much data was this? Well, the next sequence number is 406. So the actual data was 405. So if we take 4128 and we subtract 405 from that, we get 3723. So the magic number here is 3723. What does the server come back with? Well, the server comes back with, in addition to the website, right? So this is TCP data, but what is the window now? The window is 3723. How about that? So again, the reason that it's 3723 is because the client sent data. So now the other side's window, the server's window, closed down by 405 bytes. All right. Let's go back to the client's data, or the client's window. So at the end of the handshake, we had 17,520. The next packet from the client, still 17,520. Why? Because this is the client's window. It did not receive any data from the other side yet, so the window hasn't closed at all. Now, the minute the server sends some data, right? How much data did it send? Well, 560 bytes. Well, so if we take 17,520 and we subtract 560, we get 16,960. All right, so you can do this on your own calculators, but notice also that there are 2 of these. So that means that there was one chunk of 560 bytes plus whatever the next one was. Oh, it was another 560 bytes. So let's take off another 560, or a total of 1,120 bytes. So that means that the next packet that I get from the client should indicate a smaller window based on 2 packets. So let's see what it is. Well, if I take 17,520 and I subtract 1120, 560 and 560, I get 16,400, and that is the new size of the window. So we can track this right along. We can see why Wireshark is giving us these numbers, because on both sides there's been data that's been received, so the window has shrunk. Now, if we can acknowledge data going back, we can acknowledge the bytes that were sent, then we can say that the window will grow back up again. Now here, the acknowledgement number is still 406. So it's 406, 406, 406, meaning that it hasn't been acknowledged yet. Only when we acknowledge it finally from the server do we can see that the server is still not acknowledging this. Only when we see this will the window size grow back up again. And so it never grew back up again because we never acknowledged the data from the client. But if we take a look at what happened on the client side, right, we know that the window size shrunk right there to 1640. And so now what we're looking for is an acknowledgement of the data from the server. So we got a chunk here from the server, we got a chunk here from the server. Right there we acknowledged, there's an acknowledgement number right there. And so what we're expecting to hear from the client is that the window grows back up again the next time we hear from them. And there it is right there. So the minute you can acknowledge data from the other side, your window starts to grow back up again. Okay, so these were nice chunks of data, but TCP has trouble sometimes with very, very small chunks of data. Okay, so again, what we saw here is that from both sides, the receive window shrunk based on the amount of data that we had received. But when we are able to acknowledge it, the window grows back up again. Okay, so let's go back to what we were talking about. So in the upper right here, I've got all of the variables associated with just keeping track of the two window sizes. Here's what I sent you. Here's what I'm going to send next. Here's what I've sent you that hasn't been acknowledged yet. Here's the current window size. So my view of your window size, so in other words, the send window. So I'm keeping track of what I sent you and what I'll be able to send you later on, and what I've sent you that hasn't been acknowledged yet. At the same time, I've got my window. What do I expect from you? How big is my window now? Now that's just keeping track of the windows. What's this whole thing about congestion control? So again, we're concerned about sending too much data into the network and clogging it up. Now from RFC 1122, now RFC 1122 is part of the TCP/IP model definitions. And in there, it describes some of the things that the protocols ought to do and also what protocols we're using at the time. Now, what 1122 has to say about TCP is the following. Since RFC 793 was written, there has been extensive work on TCP algorithms to achieve efficient data communication. So 793 came out, and it was sort of the Wild West. We knew that we wanted to keep track of bytes. We knew that we could cause congestion, but now we've got a little bit of research, a little bit of background. So later sections of 1122 describe required and recommended TCP algorithms to determine when to send data and when to send an acknowledgement and when to update the window. So that's what we saw in packets. We're shrinking the window, and I'm getting data from you, and at some point I'm going to tell you that the window is open. Now what I could do is tell you immediately. As soon as I could, I'll open the window up, but that's not actually what we want to do. In addition, we don't want to send too much stuff into the network. Okay. So one important performance issue early on was something called silly window syndrome, which is this, it's a stable pattern, but what it does is if you send me something and I acknowledge it right away, I just give you this little tiny acknowledgement and you send me a little burp of data and then you wait. And then I send you another little acknowledgement and then you send me a little burp of data and then you wait. And this results in inactivity and poor performance in TCP. And so that's what we call silly window syndrome. Now there are a lot of applications that deal with keystrokes. So as an example, Telnet, SSH, these are protocols that send very, very small TCP packets. And so there's two things that are going on there. One is that the window can shrink and grow by very, very small sizes. So in addition to wanting to avoid silly window syndrome, what we also want to do is instead of waiting to process individual keystrokes, we might engage the TCP push flag. So we've got the SYN flag, the ACK flag, fin flags, reset flags. Push is one of those that we use to say process this data now. So in keystroke applications, we use the push flag to process things right away. And we're also trying to avoid silly window syndrome by closing down and opening up and closing down and opening up. So early on, there were a couple of algorithms that were used to describe this or what we should do about these behaviors. So Nagle and Van Jacobson's slow start are some of the early algorithms that control TCP operation. We don't just say acknowledge whenever you can, and we don't just say process data whenever you can. It's actually a little more controlled than that. So let's go back to the capture and remind ourselves about something. So way back up at the top here, when we saw that we started off with an original window of 16.384, and then toward the end of the handshake, we modified this. This is a reflection in some of the behavior of the TCP stack in adjusting itself based on what it believed network conditions might be. So this is sort of a demonstration of the implementation of some of these algorithms. Now we'll talk more about the algorithms later on, but there we have it. That's our sort of introduction to really two things that are going on. One is figuring out the whole bits in flight thing, both for me and you, but also trying to handle this idea of congestion control. So like Oliver, we're now asking for a little more. So this has been a little more on TCP windows and congestion or congestion control. So TCP keeps track of a bunch of detail. Sequence and acknowledgement numbers just sort of scratch the surface. We've got an algorithm that keeps track of all of those things that we call bits or bytes in flight. The window size can change. In fact, it often does, even if nothing's going on. Even if you're not sending data, you can modify the window on the fly. So coming up, we'll talk a little bit more about how that actually happens in some of the algorithms, the other algorithms that are used, and how those algorithms have changed over time. And that'll be RFC 5681. All right. Like and subscribe if you're with me on this journey to the top. And hey, no matter what algorithm you're using, may those packets always reach their destinations.